All right, so welcome everybody to day 3 of the data science week. So this date we have here from Johns Hopkins talking about clustering the mixture of Gaussians with unknown covariance. Yesterday we had Professor Lu from Current who talks about simulation calibrated machine learning, and we had the first workshop of our. So today the program starts with Professor Tang talking about survival analysis by ordinary differential equations, and later on we're going to have Professor Lee from the University of North Carolina, Chapel Hill. So for those who want to see some posters and short talk, which are going to be evaluated later on, so can give a look at this webpage. There are several here. You can give a look at very interesting things done by students supervised by faculty or by the students themselves. So great work. Give a look at this. You can check things there, or you can also check things through Slack chat or GatherTown. Okay, so if you go to GatherTown, you must have received the password as well. You click here, you can just go. I think the password is DSW2023, if I'm not mistaken. You go here, you enter, you put your name here. Let's write A for now. Jump around here, you have fun, you go around, you see posters. Actually, these ones are the ads for the speakers. Okay, go see things around, and then you can go here to see your posters. Okay, and short talk for those who submitted them. And here we're gonna see the documentary on ChatGPT. Okay. Awesome. So without stealing further time from Professor Tang, so let me introduce her. So Professor Tang is an assistant professor at Carnegie Mellon. She previously she was at Harvard, working with Professor Kai. And this is up to like a few months ago, I think, right? She has a PhD in statistics from University of Michigan, and before that, she studied at Tsinghua University, where she received a bachelor in mathematics. So she's interested in theory methods of survival analysis. She has great work on combining methods from differential equations and survival analysis. So without further ado, please, Professor Tang.
Thank you so much for the kind introduction, Alexandra. And also thank Alexandra and Kathleen for organizing this great event. And many thanks for inviting me being part of it as well. So today, I would like to take this opportunity to introduce the joint work with Kevin, Jiaqi, Qiaozhu, Gongjun, and Ji. Kevin is in the Department of Biostatistics at the University of Michigan. Qiaozhu is in the School of Information. Gongjun and Ji are in the Department of Statistics, and Jiaqi now is an assistant professor at in the School of Information Science at the University of Illinois Urbana-Champaign. So today I will talk about survival analysis using ordinary differential equations. So this project is motivated by a collaboration with clinicians. So at that time we were analyzing end-stage renal disease. We are analyzing the post-transplant mortality for patients with this disease. And this disease is the final permanent stage of chronic kidney disease. So basically, the kidneys no longer function on their own. And this disease is one of the most deadly and costly disease in the US. So according to previous studies from 2004 to 2016, the number of new renal disease cases increased at a median level per year, and the Medicare expense increased at $1 billion per year. So the cost is huge. And the patient with end-stage renal disease must receive dialysis or kidney transplantation. And in comparison to the dialysis, successful kidney transplantation will help improve the survival and reduce healthcare cost. But the problem is, there is a huge imbalance between the demand and the supply of donors. So now there are about like 100,000 patients waiting for the kidney transplants but just 15 of them will receive before their death. So it is very important to optimize the organ allocation, and to optimize the organ allocation, it is very important to understand risk factors associated with the post-transplant mortality. So for this study, we use the data from Organ Procurement and Transplantation Network. It is a transplant information database that has collected information for every organ donation, transplant event, and waiting list candidates. Up to now, it has more than 30-year follow-up. And the data set we used contains more than 146,000 patients, and there are also multiple covariates. For some of them, our collaborators thought that they may have the time-varying effects on the post-transplant mortality. For example, cold ischemic time, roughly speaking, it refers to how long the kidneys stay outside of the body before kidney transplantation. And expanded criteria donor, which is an indicator variable, say it is a non-ideal donor, but it can significantly shorten the waiting time. There are also various patient information like BMI, gender, age, etc. And they may have different short-term and long-term effects on the mortality. And in our analysis, the outcome of interest is time to death or graft failure after kidney transplantation. And survival analysis is an important branch of statistics for analyzing such time to event data. And record that we think the Cox model is the most important model in survival analysis. To accommodate the potential time-varying effects, we consider the Cox model with time-varying coefficients. And we tried the most commonly used R package, which is the Cox-PH package that implements the standard maximum partial likelihood estimation method for this model. However, it fails to run for such a large sample size. So first, it runs out of memory for just a few predictors. So you can see as here. And the computational complexity of the maximum partial likelihood estimation method is in the quadratic rate. So even without memory limitation, the estimated computing time can take more than 11 days. And this computational challenge motivated us to develop a computationally more efficient procedure. So here, our computational complexity increased slightly greater than the linear rate. And this efficient method is based on the new ordinary differential equation perspective. And more interested, we found that this method that was originally designed for the Cox model with time-varying effects can be applied to a wide range of other models as well. So this leads to the unified ordinary differential equation framework. And in this talk, I will introduce based on how to use the ODE notion to develop a general modeling framework that unifies many existing models as special case, and also provides opportunities to design more flexible new models. And also, based on the ODE, we're able to develop an estimation and inference procedure that can be applied to a wide range of existing models, and it is computationally and statistically efficient. And in addition, how can I lost the yeah. So in addition to the large scale, modern data set is also very complex. For example, the medical information mart for intensive care, which is a MIMIC database, it provides de-identified clinical data for patients admitted to intensive care units. And in addition to the demographic data here, there are also radiology images. So we can see here. So here is the sample for a single patient stay. So we can see that there are also radiology images, clinical notes in free text containing various abbreviations, jargon, typo, and there are also time-stamped laboratory tests of physiological measurements, such as blood pressure. They were recorded with irregular time intervals. And all such data are not in a standard vector form. And this complex unstructured data pose unique challenges for modeling time to event data. So in the second part of this talk, I will cover how we can use the neural network, extend the OD framework with neural network to make powerful predictions on this complex data in diverse format. So, let me here first give a brief introduction to survival analysis. So in survival analysis, typically the goal is to study the association between the covariates and the time to event. For example, in the kidney transplantation problem, the event is death. And our goal is to understand the risk factors associated with the post-transplant mortality. But in practice, the event may not be observed. Patients may miss follow-up during the study, or they were still alive when the study was over, and this phenomenon is referred as censoring. And there are various sensory regimes and applications. As the starting point, we'll focus on the most common regime, right censoring, in this talk. So for right sensor data, we observe the event time or the censoring time, whichever comes earlier. And we also observe the indicator of the censoring. And note that this kind of sensor data is very common. So not just limited to the survival time in healthcare, there are also various applications in other domains, such as engineering, economics, marketing, and so on. And many different statistical methods have been developed for survival analysis. It's hard to list all of them in one page, so I will mainly cover those that I will mention later in this talk later. So first is the Cox model. It's probably the most popular one, but the proportional hazard assumption is often too strong in practice. So many alternatives have been proposed, such as accelerated failure time model, referred as AFT model, and the Cox model with time-varying coefficients, also the linear transformation models. So different models make different assumptions on how covariates are associated with the event time. Also, different estimation methods were developed for these models correspondingly, such as the partial likelihood-based method for the Cox model, least square rank-based method for the AFT model, non-parametric MLE, etc. have been developed subsequently. And we are going to see how the ordinary differential equation notion helps to unify these existing models and also develop an estimation inference procedure that can be applied to many different models. But beyond the unification merit, we also want to know that, to comment on what the differential equation, this new perspective, bring to survival analysis. So first, this unification, this unified framework also allows us to develop new models. So we'll introduce a new class of ODE models that is more general than the existing models. And also a neural network extension later. And second, or more importantly, after introducing the ODE notion, we are able to develop a computationally efficient procedure. And this estimation procedure is widely applicable and easy to implement. That is thanks to the numerous efforts done in applied mathematics about the numerical ODE solvers. And third, we also know that after introducing the ODE notion, actually introduced the new theoretical challenges for statistical inference, and we developed a general new M theorem that can be applied to study the asymptotic distribution of the estimates on the various ODE models. Okay, so let me start with the unified modeling framework. So here are some key notation used in survival analysis, and we use the lowercase lambda to denote the hazard function. It describes that conditional on the survival up to time t, the probability of experiencing the event within a very short time interval delta t, and once delta t goes to 0, it becomes the instantaneous rate. So because of this practical meaning, This hazard function is a very popular modeling target in the literature. And here we use the capital lambda to denote the cumulative hazard function. And either the hazard function or the cumulative hazard function can uniquely determine the conditional distribution of the event time given covariates. For example, the exponential distribution function has a constant hazard. And in the proposed OD framework, we also model the hazard function, but we look at it from a different perspective. We view it as the derivative or the dynamic change of the cumulative hazard function, and we model them together using the ordinary differential equation. Record that in the generic form of the first order ODE, the derivative of y is determined by a function of t and y itself, and this function may depend on the parameter theta. In our ODE framework, y is the conditional cumulative hazard function. And the derivative of the cumulative hazard function will depend on the time t and the cumulative hazard as well as the covariates. So here, the function h determines the dynamic change of the cumulative hazard, and its form needs to be specified. A different specification of function h leads to a different OD model. And we are going to see several examples in the next few slides, where we choose the form of h for easier interpretation. And its initial value at time 0 indicates that an event always occurs after time 0. Then given the specified smooth function h and initial value, the existence and uniqueness of the solution can be guaranteed. In other words, the cumulative hazard function, or say equivalent to the distribution of the event time given covariates, is uniquely determined. Okay. Yeah. So as I mentioned earlier, a different specification of function h leads to a different OD model. Here we illustrate the proposed OD framework unifies many existing models as special cases. First is the Cox model. It assumes that each covariate has a multiplicative effect on the hazard. And we know hazard is the derivative of the cumulative hazard, so it is straightforward to rewrite the original form as an OD. But the second example is a non-trivial example, accelerated failure time model. When it was originally proposed, it assumes that the log transformed event time is linearly associated with covariates. And the error distribution can either be specified in the parametric model or unspecified in the semi-parametric model. And it turns out that we can rewrite the AFT model as an ODE. So there is a one-to-one mapping between the function Q and the error distribution. For example, when the function Q is a power function, then the exponential error follows a Weibull distribution. And we also find that rewriting the AFT model as an ODE, it provides new interpretation in terms of the hazard. Specifically, given the current cumulative hazard, covariate X have multiplicative effects on the hazard. And beyond the effect of covariates, if the function Q is monotonic increasing, then it suggests that a higher current cumulative hazard leads to a higher increase in itself. And another example is the linear transformation model. It assumes that after certain transformation per psi, the event time is linearly associated with the covariates. So it includes the Cox model and the AFT model as special cases, and we can also rewrite it as an ODE. So there is a one-to-one mapping between function Q error distribution, and there's another one-to-one mapping between function alpha and the per psi transformation. And different specification.
Can I ask you a question?
Yeah, sure.
So the function Q is it explicit if and only if you can write explicitly the cumulative hazard function?
Oh, sorry. Can you say again?
Yeah. So I'm asking when the function Q can be written explicitly. So I'm guessing the same times where when you can write explicitly the cumulative hazard function. Am I correct?
So Q is determined by the error distribution. So once we have a we know that we can write explicitly the distribution of error distribution, then we can, there is a formula has already been given in our paper that we can derive the explicit form for the function Q.
Okay, got it. So let's say I use normal distribution. I can get Q explicit.
Yeah, we can get the Q explicitly.
Right. Oh, the reason for which I'm asking if they're in explicit form is that then if they're not in an explicit form, then it's more complicated, I would say, right? If you couldn't write Q in an explicit form, it becomes more complicated, I'm guessing. But since there is not a problem, then I think it's fine. Yeah. But I just wanted to know if the ODE was explicit in practice.
Yeah, we do have a provide explicit mapping from the epsilon. So once we have the state survival function of the epsilon, then there is a very clear form from the survival function to the Q function.
Thank you.
No problem. Oh, okay. As I mentioned, like there's a one-to-one mapping between the function Q and the error distribution and function psi and the alpha function. And the different specification of the transformation have been considered. For example, like Cheng, Fang, and Sheng et al., they consider unspecified transformation function with a specified error distribution. And in that case, we have an unspecified alpha function with a specified Q function. Okay, yeah. So in addition to these three examples, the proposed OD framework also covers many other existing models, such as the Cox model with time-varying coefficients, additive hazard model, accelerated life model, etc. And so far, we have introduced a modeling framework based on the OD notion, and we see that it has a good unification merit. And this merit is the foundation for the widely applicable estimation method that we will introduce later. And by rewriting them as an ODE, we see that it can provide a new interpretation in terms of the hazard. Also, it offers opportunity to design more flexible models, such as a new class of OD models that covers the previously mentioned model as special cases. And next, we are introduced that we have been able to develop a widely applicable procedure for estimation and inference. So to illustrate the estimation method, we consider a new class of ODE models. Recall that in the previous long table, we showed that many existing models can be written as ODE. And this new class of ODE models is a more general form and includes the Cox model with time-varying coefficients and the linear transformation model as special cases, so as to include the Cox model, AFT model, proportional odds model, etc. And here we have two types of covariates, X with time-independent coefficient beta and Z with time-varying coefficient eta. So given one's current cumulative hazard function, both covariate X and Z have multiplicative effects on the hazard. Right. Oh, okay. And here, alpha and Q are two positive functions which are unspecified. So different specification can be considered, but we leave both of them to be unspecified to make the model more flexible. When both of them are unspecified or unknown, the model is not identifiable, and we have developed additional constraints for identifiability. So we propose to estimate these parameters, we propose to directly maximize the full likelihood function. So given this IID data and uninformative sensory, under the OD model, the log likelihood can be written as follows. Well, it looks a little bit complicated, but the key message is that it contains the solution of the parameterized ODE. The ODE is parameterized by beta, alpha, Q, and eta. So there are two things that need to be addressed in the maximum likelihood estimation. So first, parameters alpha, Q, eta are functional parameters. And second, how to evaluate the objective and its gradient when it contains the solution of the parameterized ODE. And this is non-trivial. So to accommodate the functional parameter, we use the spline-based CFMLE, which is commonly used for non-parametric function estimation. And we maximize the likelihood over the finite dimensional sieve parameter space. For example, we can construct the sieve space using local polynomial splines and basically some piecewise continuous function. And we approximate these functions by the linear combinations of spline bases. And to make sure the functional parameters alpha q to be positive, we consider their log transformations. And then we maximize the likelihood with respect to beta and these coefficients using gradient-based optimization algorithms. Then in the gradient-based optimization algorithms, how to evaluate the objective and its gradient when it involves the parameterized ODE, which is unconventional. So here we use the numerical ODE solvers, which has been widely studied in applied mathematics. And we will not give the detailed formula of the algorithm, but just describe the overall procedure. So specifically in each iteration, given the current estimates of beta and these coefficients, to compute the objective for each subject, the cumulative hazard function, we use the numerical ODE solver, we solve the following ODE. And then to compute the gradient with respect to these parameters, we solve another ODE, which is not shown here. It is derived by the local sensitivity analysis. So roughly speaking, local sensitivity analysis is the assessment of the impact on ODE solution, where there is more variation on the ODE parameters. Then in the gradient-based optimization algorithms, basically we solve one ODE to evaluate the objective and another ODE to evaluate the gradients. And the evaluation of objective and gradients can be parallel for independent individuals.
Can I ask another question? Do you mind going back to the maximum likelihood?
Oh, sure. Let me go back. Yeah. Do you want to go back to here?
Please one. Yeah, this one. So my question is this. My understanding is that it's hard to estimate the derivatives. But these equations can be transformed into Duhamel's form. When you transform them into Duhamel's form, in practice, instead of estimating derivatives, you estimate integrals. And that should be simple.
Oh, sorry. Okay.
Yes. So I'll tell you again. I'll say differently, right? So this type of ODEs looks to me that can be rewritten in Duhamel's form, namely in integral form in practice, in a weaker form, which is integral. And my question, the reason for which I mentioned this is that in general, it's simpler to estimate integrals than derivatives. So if instead of having a likelihood directly on the ODE, you have a likelihood on the Duhamel's form of the ODE, it might be that some of the estimation procedure is simpler, because instead of estimating derivatives, you end up estimating integrals. And those integrals are well defined because you're assuming Lipschitz continuous functions, my understanding is. So those integrals are well defined. So you're going to end up having a little bit more stable procedure, I believe, if you go to the, if you estimate not directly the ODE, but the Duhamel's version of the ODE.
Yeah, I would say that may be a good alternative to do that. So for here, we consider this ODE is basically comes from we want to model the hazard function. That's because that's a very popular modeling target in the literature and it has nice interpretation. So that's why we end up with this ODE. So, and here, as you mentioned, like actually this one can be viewed as the integral of this part. So I would say that may be an alternative approach. If you think that model interpretation is also a good choice, then we can try that one as well. Yeah. Sorry.
Yeah, it's good. Yeah, thank you.
Thank you. Okay. Mhm. Okay. Right. Okay. So, I also want to, yeah. Okay, yeah. And so we propose these gradient-based optimization algorithms to maximize the full likelihood. And this approach is applicable to a wide range of models, including the previously mentioned ones. And for certain classical models, such as the Cox and AFT model, many efficient estimations have already been developed. But for more flexible models, such as the Cox model with time-varying coefficients and the general linear transformation model, where both the transformation function and the error distribution are unspecified, their existing estimation methods still suffer from computational challenges. And next, we'll see comparisons with them. So for example, the first example is the comparison with the maximum partial likelihood estimation method for the Cox model with time-varying coefficients. So in the maximum partial likelihood estimation, in their objective, for an uncensored subject M who experienced the event or who died at time t m, evaluating its partial likelihood requires access to all other subjects who survived longer than time t m, so which is also known as at-risk set. And then in the partial likelihood, we take the product of all uncensored subjects. So the computational complexity is n times d. So here n is the sample size, and d is the number of uncensored subjects, which can be proportional to the sample size. So the computational complexity can be as large as the quadratic rate. And in comparison, our estimation method, the complexity is n times k. Here, k is the number of spline bases, which grows sublinearly in rate n to the power v for convergence guarantee. And in our numerical status, v is chosen to be 1/7, which is implied by our theory. So the overall complexity is slightly greater than the linear rate. Oh, yeah. Okay, so here is the numerical example. We compare the proposed CVMLE with the partial likelihood based estimator. And on the left, this is the log mean square error with respect to the log sample size. And we can see that these two methods perform almost identically in terms of the estimation accuracy. However, in terms of the computing time, the proposed CVMLE is much more computationally efficient. So as the sample size grows, the relative computing time of our method increased almost linearly, but that of the partial likelihood-based estimator increased in the quadratic rate. And here is another example. We compare the rank-based method for the general linear transformation model, where both the psi, the transformation function, and the error distribution are unspecified. So in our case, both the function q and function alpha are unspecified. And to the best of our knowledge, the only existing estimation method for this general model are the two rank-based methods. So first, partial rank method. It needs to calculate the pairwise comparison between each uncensored subject and all other subjects in their at-risk set. So again, the computational complexity is in the quadratic rate. And moreover, the objective function involves this discontinuous indicator function, which makes this method numerically unstable. And there is a follow-up method called smooth partial rank method, which replaces the indicator function by a smooth function SC here. C is the hyperparameter. And our numerical experiments suggest that this method still does not completely address the numerical challenges and sensitive to the hyperparameter C. So here are some numerical examples. When we compare the proposed CVMLE with the smooth partial rank method. And the success rate here is the number of successfully converged replications, the proportion of it. So our results suggest that our estimates are at least as good or better than the smooth partial rank estimates. And their estimates are quite sensitive to the hyperparameter C here. Also, in terms of numerical stability, the success rate for ours is almost 100%, but that for the smooth partial rank method becomes more unstable, especially for the large sample size. And in addition, like this method requires the weighted bootstrap for inference, so we can see that the success rate is even lower. And here we also compare the computing time of our method with the smooth partial rank method, and ours increases in a much slower rate than the smooth partial rank method as the sample size grows, which implies that the proposed estimation method is computationally efficient for large sample size. So to briefly summarize, our estimation method can be applied to a wide range of OD models, and it has computational or numerical advantages over existing estimation methods for some flexible models. And from a practitioner's perspective, it's also easy to implement on top of well-established OD solver, the software packages of OD solvers. Okay. But it's also important to quantify the uncertainty of our sieve estimator for valid statistical inference. So in particular, our proposed sieve estimator belongs to the semi-parametric M estimation setting. So specifically in the semi-parametric M estimation, we have both finite dimensional parameter beta of interest and other nuisance infinite dimensional parameters. So here, the M estimator refers to the estimate that maximizes the sample average of the objective function M. And in our case, the objective M is the log likelihood. And under the general class of ODE models, we have both finite dimensional parameter beta of interest and infinite dimensional parameters gamma, eta, and g. So it can be viewed as a semi-parametric M estimator. Oops. Sorry. Okay. Yeah. And many asymptotic distributional theory have been developed for semi-parametric M estimation, and they can be applied to study some simple OD models. For example, in the Cox model, right, we have parameter beta of interest, and the gamma is the nuisance, infinite dimensional parameter, and they are well separated. And this case can be covered by the theory developed by Werner and Zhang in 2007. And another example is the accelerated failure time ODE model. So this case is a little more complicated because the argument of the function g is the cumulative Hasse function, which depends on the parameter beta. So in this case, the finite dimensional parameter of interest, the beta, is bundled with nuisance infinite dimensional parameter g. So they are bundled together, which is a more complicated case. And Cheng and Di and I have developed general theory that can be applied to study the asymptotics of the estimator from this case. However, for more general OD models, such as the general linear transformation model, where both the function gamma and g are unspecified. So in this case, the parameters are bounded in the more complicated region. So recall that the argument of the function g is the cumulative Hasse function. And now in this time, it depends on both the finite dimensional parameter beta and infinite dimensional parameter gamma. So in this case, the best of our knowledge, existing asymptotic distributional theory cannot be directly applied for valid inference. So here we develop a new general, sieve ML theorem that can be applied to study the asymptotics of the semi-parametric M estimator. So in this case, we have the finite dimensional parameter beta of interest and also infinite dimensional parameters gamma and d. And also there's a nuisance parameter that is bundled with both finite dimensional and infinite dimensional nuisance parameters. And our proposed general Sieve-ML theorem can be applied to study the symptotic normality of the estimate of the finite dimensional parameter beta. And this theory is important to quantify the estimate under the flexible ODE models. And now we apply the proposed general Sieve-ML theorem back to the Sieve estimator on the ODE model. And we use the theta naught to indicate the true parameter and the theta n hat to denote the Sieve-MLE. So we first established the overall consistency of the entire Sieve estimator, which include both the finite dimensional parameter and infinite dimensional parameters. So here the convergence rate is similar to the optimal convergence rate of the non-parametric regression setting. And then by applying the proposed general Sieve-ML theory, we're able to derive the symptotic normality of the finite dimensional parameter beta n hat. And note that because of the ODE model structure, the proof of consistency and the symptotic normality requires non-trivial efforts and relies on fundamental theorems of ODEs. Okay. And now we're applying the proposed method back to the post-transplant mortality problems as I introduced at the beginning of this talk. So recall that our goal is to study the risk factors associated with the post-transplant mortality. And the data set we used contains more than 146,000 patients. And to investigate the time-varying effects of the potential risk factors, we want to fit a Cox model with time-varying coefficients. And we mentioned that the existing R package failed to run for such a large sample size, and now we use our proposed estimation method. And by fitting a more flexible model with a large sample size, we are able to observe new interesting results. And here, here are some estimated time-varying effects for for 3 covariates, and this blue dotted curve is the estimated function, the time-varying coefficients, and the red curves are the 0 baselines, and these dashed yellow curves are the estimated pointwise confidence intervals. So they were obtained by inverting the estimate information matrix of all parameters. So for example, our results for the high code ischemic time show that it is initially a risk factor for mortality, but diminishes gradually after a couple of years. So special cares are needed to improve the short-term results. And our results for obesity is actually interesting because we found that obesity improves the survival in the short term, but becomes a risk factor after long-term exposure. Because typically for the general population, higher BMI is associated with higher mortality. However, in the chronic kidney disease, for patients with kidney dialysis and kidney transplantations, higher BMI has been associated with better survival, and this has been labeled as reverse epidemiology. So our results are consistent with the previous findings. And this signal may be canceled out if fitting a simpler model, such as the Cox model, with only time constant effects. And we also notably found that there is a jump in risk of taking the expanded criteria donor in the short run. So when the suboptimal donor becomes available, patients and physicians must decide whether to accept the offer, and special care must be dedicated to improve the short-term result. Okay, so in the first part, I have introduced a flexible modeling framework based on ODE notion and a computationally and a statistically efficient procedure for estimation and inference. So next, we'll see how the flexibility of the proposed ODE frameworks helps to accommodate data in diverse formats, and these help us to make powerful predictions. Recall that at the beginning, we mentioned about the MIMIC database, which is collect data for the intensive care units. It includes the radiology images, clinician text notes, and the longitudinal lab test results. And they're all not in the standard vector form. So how to perform survival analysis on this complex data set? And deep neural networks have shown their superior prediction performance on this data. And then stemming from this, a natural question to ask is, how to incorporate the neural networks into survival analysis? And the answer to this question is actually not obvious. Unlike learning neural networks for classification tasks, there are unique challenges in deep learning survival analysis because of censoring. So there are a few recent works in deep learning survival analysis, and early works adapted the Cox model to allow the nonlinear dependence on the features. For example, the DeepSurf replaced the linear combination by a neural network. And subsequently, Cox time further considered the interaction between time and features. And these models are all trained by maximizing the partial likelihood. However, there is a critical problem when combining the partial likelihood and the deep learning models. In particular, in deep learning, stochastic gradient descent is particularly important for efficient training on large-scale data. So roughly speaking, at each gradient descent step, stochastic gradient descent randomly samples a subset of data points to estimate the actual gradient when using the full data. So it helps greatly reduce the computational cost. However, in the partial likelihood for uncensored subjects, the partial likelihood for this subject requires access to all subjects in the at-risk set. So stochastic gradient descent algorithm cannot be directly applied, and this becomes a serious limitation for partial likelihood-based deep learning. Right. Yeah. And alternatively, we consider to maximize the full likelihood, because in this case, stochastic gradient descent can be naturally applied for independent individuals. So for specifically given this IID data, so here delta is the indicator of the censoring, and the full likelihood is given here. So because of the censoring, for some subject, we have both little lambda and big lambda. And for some other subjects, we only have the big lambda. And note that the big lambda is the integral of the little lambda. So it is unavoidable to compute the integrals in the likelihood. And moreover, if we model the little lambda as a neural network, there is no closed form solution for the big lambda as well. So these are the unique challenges in maximizing the full likelihood in deep learning survival analysis because of the censoring. And there are some works that try to avoid computing the integral. So they propose to discretize the continuous event time with pre-specified time intervals so that they can simplify the integral to a cumulative product. However, this may cause information loss and introduce the breakpoints as additional hyperparameters, which usually need to be fine-tuned. So instead, we propose a flexible continuous time approach that is based on the ODE framework. So we address the computational challenge by a numerical approach. And record that in our ODE framework, function h determines the dynamic change of the cumulative hazard. And in the proposed ODE neural nets, like ODE approach, the function h is modeled by neural network. So it takes the time t, the current cumulative hazard, and features as input and returns the dynamic change of the cumulative hazard function. And here we use the theta to denote all the parameters in the neural network. And we know that this method can easily accommodate the data in diverse formats by simply adopting different encoders. For example, we can use recurrent neural networks for longitudinal laboratory test.
Can I ask you a question?
Yeah, sure.
About the previous slide. So what bounds do you have on h of theta? Like, so what I'm wondering here is that, so do you have any bounds on the asymptotic growth of h of theta when, yeah, exactly, that's it. So do you have any bounds on the asymptotic growth of h of theta? Like, do you have any bounds on the function h?
Yeah, so here we for the second part, we will not provide the asymptotic results for the parameters. Here we almost view h theta as a non-parametric functional estimator. So previously we have the coefficient of covariance of interest. That's our target parameter, and our general theory can be used to apply to study the asymptotic normality for that part, for the finite dimensional parameter. So here in this case, this is more like a non-parametric approach. So we haven't provide asymptotic results.
Is it bounded in L infinity? Is it bounded in L infinity, for example? H, the function H?
So is there a bound for infinity?
Yeah, in L infinity, like in the sup norm. Is H bounded in the sup norm?
So far we haven't obtained that result, but I think that would be an interesting direction to explore.
Well, the for which I'm asking is I want to make sure that long term, right? This ODE well behaves, right? So if lambda might be growing, right? But if H is bounded, then I'm good, right? So that's what I'm trying to figure it out. If there is a long-term good behavior of the solution of this ODE.
Oh, are you asking if the H is bounded, or are you asking
about
the convergence guarantee?
H is H.
I see. Yeah. Oh, sorry. Because I was so like you were asking about the theoretical results for the estimator. So here for H, we do make certain assumption whether it's a Lipschitz continuous smoothness guarantee. So in that case, because we want to guarantee that the ODE has a unique solution in that sense.
Also long term. So I'm guessing that at a certain point people die. So the ODE is gonna, you don't care too much about asymptotic to plus infinity, right? But you want to avoid something like a blow up before the actual the event, right? So you would need some sort of bounds on H. That's what I'm wondering, right?
Oh yeah, so like at least like for theory or like in practice, typically there is an upper bound of the time in terms of like say the follow-up time. So in that sense, as long as during that fixed the time interval, the bounded time interval, we have the certain smoothness guarantee, then H would not be super large. So because our goal is not like to make the prediction for the infinite time. Basically, there is typically upper bound of the time interval that we are interested in.
So the only worry that I was having is I suppose that the solutions of the ODE blow up before the time of the event. Then there is a problem, right?
Yeah, that's like yeah, like basically if our assumptions are does not hold like in practice, then it may be a problem. Yeah.
Right. Thank you.
That's a challenge for the ODE. So ODE, yeah. Okay. Okay, great. Okay, so to estimate the parameters here, we use the proposed estimation procedure to maximize the log likelihood, and stochastic gradient descent algorithms can be used to make the algorithm more scalable. And we use the local sensitivity analysis again to compute the gradients and using the GPU-based implementation for faster training. And we have compared the proposed method with the state-of-the-art neural network-based method on 3 real-world datasets. And here is one example. We applied the proposed method for ICU mortality prediction. And record that this MIMIC is a benchmark database for machine learning in healthcare. It is publicly available and provides de-identified clinical data for patients admitted to intensive care units. And this data set contains around like 35,000 patients who are still alive 24 hours after admission to the ICU. And the outcome of interest is the survival time, and a patient is censored if there is no death record in the database. And the corresponding censoring time is just the duration until the last time of being discharged from the hospital. And here we use the feature extracted from the first 24-hour clinical data, and there are 5 time static features such as demographics, admission type, etc., and 15 time varying features, and we use the recurrent neural network as the encoder for this part. And we compare the proposed method with 4 state-of-the-art neural network method, and this table summarizes their differences. And in particular, DeepServe and Cox time are 2 continuous methods and maximize the partial likelihood. And DeepHeat and NNet are 2 discrete time methods. And this table summarizes the C-index and Brier scores for this method. And the C-index measures the discriminative performance similar to the AUROC for binary classification. The higher is better. And the Brier score measures a combination of the discriminative and the calibration performance. So we can see that both the proposed Soden and the discrete time method, the DeepHeat, have shown strong discriminative performance. So they significantly outperforms the other method, but DeepHeat is less calibrated than ours. And from a practical perspective, the differences, while the differences are statistically significant, but their absolute difference are relatively small. But we do see that using the neural network approach have a substantial advantage compared to the standard Cox model. Okay, so to finally briefly summarize our contribution, we have introduced the ODE notion to survival analysis, and this ODE notion brings many benefits. First, it unifies many existing models as special cases, and also provides opportunity to develop more flexible new models. And we also, it also allows us to develop a widely applicable procedure for estimation and inference, and it is computationally efficient and numerically stable than many existing estimation method. And we also developed a new general CFML theorem that can be applied to study the asymptotics of the estimates under various ODE models. And finally, we have shown that the proposed framework can naturally accommodate neural networks for complex data. In the code of our approach, these 2 parts are publicly available on the GitHub. And I would like to thank you for your attention, and would like to take any questions if you have.
Awesome, thank you very much. So, is there any question? So let me ask one more question, right? So is there an intrinsic reason for which these ODE models, this ODE perspective gives an advantage computationally?
Yeah, so I would say the reason is actually because of the censoring. So as I briefly mentioned in this part, so because in the standard like classification setting, we don't have such a censoring indicator. So in that sense, the objective function would not involve both a function and its integral, or say a function and its gradient simultaneously in the objective. But in survival analysis, censoring is something that we must handle. And Because of the censoring, we have both the little lambda and the big lambda in the likelihood. And to avoid that, many existing methods use the partial likelihood, but it also, the computational complexity is in the quadratic rate. So that's the reason that, because we noticed that their objective requires the calculation of the integral, it's very natural to introduce or to model the cumulative function and the hazard function together as an ODE. And then we can naturally use the ODE solvers to evaluate both of them. And that's the, I think, the main computational challenge. So basically, we reduce those quadratic computational complexity in partial likelihood to the linear complexity when we're using the full likelihood. And we provide a method that can evaluate the gradient and the integral simultaneously in the objective function.
Yeah, is it actually no? Is it actually equal to 0.1 or is it just a logarithmic term?
Oh, sorry, zero.
So the approximate linearity in the computational complexity, is it really 1 plus 0.1 or it's something like logarithmic?
Oh, so so here in this part, yeah, let me show you here. Okay. Yeah, I do want to briefly mention. Yeah, so basically in our case, we do have like a 1 plus V, and the V is required for convergence guarantee, in the sense that here we're actually using the finite dimension of basis function to approximate the non-parametric function. That requires the number of spline bases to increase with the sample size. So in that sense, V is a term that depends on N, but it's very small. It's almost in the log sense. Yeah.
Other questions online?
I have a question.
Yes, please.
So I'm not in academia. I work for a credit union, and I've had a problem that I've been working on where it's a similar data set to what you described with the your survival model, where it's time varying covariates, and it's a survival. What it is, it's trying to predict when they'll pay their loan off. Right, so they have a set term, 5 years, 6 years, whatever. I think it goes up to 15, and it's just they make a payment every month, and you try to predict the probability of when they'll complete their payment, and then try to model it as a survival model. Like I said, time varying covariates, like the credit scores are changing, they're delinquent the last month, et cetera, factors like that. And what I found first, I haven't found much literature. Published literature dealing with these problems with time varying covariance survival models. But I've tried several different methods, and it's not the prediction of survival time is not rapidly decreasing to 0 when the loan term is coming up, like you would expect, right? There's a set time. The vast majority of people are going to finish their payment on time as whatever in that period, the 17 months. So it's really high likelihood, just observed fact that survival isn't going to be much more than that at that time period. But when I'm predicting something at 12 months and it's going to go to 60 months, as I'm getting out, doesn't decrease fast enough. Right? It's going to be way off on the end of the time period when I'm doing a prediction way out from when the actual payoff period is. And like I said, I've done several. I did parametric, the Cox model. I've also did a random forest type thing. It was a paper, discrete time, dynamic estimation with random forest for discrete time survival data, where they're using random forest, but again, they're using the same data set you would build for a time varying Cox model where you have every step of time. So first I'd ask, did I describe my problem accurately to you? And then second, any idea of why I'm not observing? I know this isn't really related to your topic, but it's the same data set. Have you seen anything like this where you've got your large data set, the time varying covariance, and you're not, I guess it's, well, long survival times where, when they get to 100 years, if you put that in your model, it's still saying they have a 50% chance of survival. Have you seen anything like that in it with your data and this type of data?
Yeah, I think that there are a few recent developments in terms of dynamic deep heat as well as some other dynamic. There is another OD model as well, so they can handle the time varying covariates. That's the case. That's the case. Based on what I heard from your description?
Right.
Is that you want to make dynamic prediction when your covariates may change over time?
Right.
And in that sense, there are some recent developments. One thing is known as the dynamic deep heat, which can handle this case. I think that's kind of different from the problem I have described, because so far, yeah, here we do have the time varying covariates, but we do not use the information after time zero. So in your case, it's more like, okay, at time t equals to 1, I have new
Right.
covariates available.
New
And
setting,
then we
right.
want to make the
Right.
new prediction. Yeah, so that's a relatively different setting, but there are recent developments. So one thing you can probably search is the dynamic deep heat.
Okay. Thank
Yeah.
you.
Awesome. Other questions? Well, if not, let's thank Professor Tang again for a good presentation. Thank you. Thank you very much. Thank you very much for the time. And I think we are gonna resume in 50 minutes, another room, but same WebEx link. Okay. Thanks a lot. Thank you.
Thank you.